My name is Pedro Flecha. I come from Lima, Peru. First of all, I want to thank Jerry Pollack for inviting me here. I was not going to speak about this, but I think it's proper to say, to speak about the methodology that we have been using in Peru for this. It may sound transgressive to the scientists here, but for us Peruvians, it's a traditional way of looking at things. I mean, Peru is, the Central Andes are a culture that has 8,000 years old, and this methodology has been used for thousands of years. The methodology is very simple. Look into a need of something. The first point is observation. The second is experimentation. The third is to start building a mutant hypothesis. So this hypothesis starts to generate by experimentation some anomalies. But if the anomalies repeat, then they are incorporated to the hypothesis. But they are always free radicals. You live always the free radicals. The anomalies not resolved because it's a complex country. We have the sea, we have a coastal desert, we have the high Andes and the Amazon. So an hypothesis, a fixed hypothesis, may be good for the desert, but not good for the high Andes, neither good for the Amazon, and the reverse. So it got to be a very flexible hypothesis that never ends. So it is a different way of looking at things. Also, in the tradition, we avoid, this is the traditional way, it's a technological thing at the beginning. It is avoided to count things and measure things. The thing is, geometrical proportions. It works by geometrical proportions, not by numbers. Numbers were used always as counters. So, okay, so I am going to start with this. This is, what I am going to talk is a macro scene compared with the micro scene, I think, but there are a lot of coincidences. This is the specter of the global ultraviolet energy potential. As you can see in the tropics, it's very, very high. And if you see in the Andes in South America, it's the highest one. Also with Papua New Guinea. What we are talking about is that we are talking about 18 UVI index in that zone, right? The UV index is not proper. I mean, has been made for sunburns and that type of things, but in energy terms, it's different. But you see there is the tropical belt, and I would say that for our purposes, the thing I'm going to say is that it is around 14, but our technology say if it is 10 on average above, then it is a potential thing. This has to do with the ozone layer. I mean, UV is always related to the ozone layer. So at the left, this is a recent, October 19, you see the ozone layer on the left and the ultraviolet intensity on the right. We are starting the high UVI season. So you see there that the ozone layer follows the Andes Mountains and also the ultraviolet. Already in the highest zone, which is Cusco and Puno, is 15 already, right? I mean, what is considered in this UV index is that anything above 10 is extreme, right? So we are talking, it's very extreme, and this in 1 month is going to be increased. And we hope, well, what is going to happen in December, the coastline is going to be about 17, right? This is the Peruvian coastal desert, which is our objective now. It never rains, never. The humidity, the atmospheric humidity is on average 75%, and it goes as high as 98, and not lower than 50 or 60. Temperature is normal. It's a tropical country, so it is on average 20 degrees Celsius. It goes, the lowest is about 12, the highest not higher than 34 Celsius. Insolation is quite big. It's around 6 to 7 kilowatts hour per square meter per day. UVI is 10 in winter, 17 in summer in the coast. In the highlands, it's much over that. I mean, it gets to 25. No? The evapotranspiration in the desert is very high. It is 1 to 2 meters per year. And the land availability in the desert, obviously, are million hectares. Our initial objective was desert afforestation by the use of succulent plantations, which means aloe or opuntia or some other plant that capture water from the atmosphere. And the needs of water are only for making some small roots that then don't get displaced by the wind. The water resources for the desert that is the processing of the succulents. For instance, I am going to describe that later, and the atmospheric water capture by the use of hygroscopic salts like calcium chloride. The UV capture is coming from natural aloe liquids. What happens is, and we have tested that the aloe plant, I think everybody knows what aloe is, in the conditions of the Peruvian desert needs, which is very stressful, needs to generate a lot of photosensitizers and a system of enzymes that keep the plant survival with all these harsh conditions. This is a conclusion, a preliminary mutant hypothesis that we found, and that's the reason why I contacted Jerry some months ago, that we found that in our water capture, atmospheric water capture, that is mainly done in the night, at the early morning, there were floating little lyses in the solution, little tiny cover of that. And we call them ice lights, okay? They are funny because they are lighter than water. Second, like normal water, they have a kind of hydrophobic behavior. I will going to explain that after. And it sublimes and deposits. So if we, for instance, for water harvesting for the atmosphere, we got to take the water collected during the night before 10 a.m. Because after 10 a.m., it goes out, right? And how we are doing this on the photochemical thing, we deconstructed the aloe plant. I will keep the anecdote to the end if I have time. But the aloe plant is a funny plant. Well, it's not a funny plant. It's like any succulent. It's very similar to a plankton. Let's put it in general terms. Okay, plankton is very similar to aloe in their mechanism, except the plankton is surrounded by water, and aloe has the water inside, right? But there's a mechanism of survival, which is acquiring solar radiation, especially UV, transforming that into hydrogen peroxide via the photosensitizers. The first step is to activate oxygen, and then the SOD, superoxygen dismutase, change that to hydrogen peroxide, and then you have the catalyst that decompose the hydrogen peroxide, right? So the plant regulates, according to the climate, an equilibrium of hydrogen peroxide in water. Why? Because the blending of that raises the evaporation point and lowers the freezing point. So it's a type of material that has more flexibility. But the plant cannot have too much hydrogen peroxide, so the catalase enters there and decomposes that. These are the two plants, the Opuntia, which is a cactus, and on the other hand, Aloe, well, both are succulents. So we are going to use the Opuntia for water resources, and the aloe vera for the UV harvesting. In the bottom part, you have what an aloe plant is. The liquids in the aloe plant are around 98-99%. It is located in the parenchyma, which is are little bags of liquids inside the parenchyma, and in the cover, under the cover, there is the latex or sap of aloein, which is photosensitizes, is an anthrachinone, which is the photosensitizer, and also the enzymes that do the work. Now, getting into what is the natural process, one thing we exclude is to take the least variables that possible to get to the core. For instance, we depart from the idea that, for instance, temperature, wind are effects and not causes. So we go to the causes, which is the intervention of UV with water through in the natural system with chlorophyll, and so you get the UV, and then you have the shifting between O2 and O3 and ozone. Then you get the chlorophyll, and then it is a system of water plus reactive oxygen species, and it goes up and down, up and down. So that's the system. So our process is the same thing, except that we extract the hydrogen peroxide before it decomposes by the same UV radiation. This is the photochemical part. I am not putting a chemical formula, but just a succession of things. This is a natural process in which UV via SOD gets into hydrogen peroxide. Then the UV also decomposes the hydrogen peroxide in water plus oxygen plus heat. And this is the UV intervention, but when there is a catalase, the same thing happens, right? Our process is the same, except that we depress the catalase activity by making a special brine and a special design of how to make the brine. So, and we extract the energy that was archived from the ultraviolet by cementating it in lime. No? So we get that oxygen that was captured and that energy into a solid that can be separated from the solution. This is a picture of how it works in the whole system. You have UV, visible light, and then oxygen, which is the atmosphere, and there is a brine here with the aloe plant photosensitizers and enzymes. So it is H2O2 generated. We use lime to precipitate it, but the lime comes from the limestone. So you got to calcine the limestone to obtain the lime, but the CO2 generated is captured by the plant. So it makes a kind of a virtuous circle where it's carbon neutral. And the brine is recycled with the enzymes and photosensitizers with very minor losses. Also, well, this is a disquisition that it is carbon neutral, but I'm not going to stand on that. For instance, this material, the calcium peroxide, can be used to capture CO2 and at the same time generate free oxygen. So for thermal plants that burn coal or fuels, all type of fuels, is good because it absorbs the CO2, in a neutral as calcium carbonate and generates oxygen that pays the trip from the place of production to the place of use, because the oxygen is used for power generation. Well, this is the basis of our process, but we want to put an example. This is still a mutant hypothesis, right? So the biggest UV photochemical cyclical recurrent event in our planet is El Niño. We have had a tremendous Niño in February this year. We have said that incoming UV radiation gets absorbed by catalysts and water in forests, plankton, and algae, making reactive oxygen species that act as oxygen capturers, right? So there is a dilution of atmospheric CO2 into the water. But as there are this system, it captures that oxygen and fixes that in hydrogen peroxide, so there is more room for requiring more oxygen. So it is a kind of a storage. You know? This has to do a lot with ozone, the high and low UV, and that is non-linear, has a non-linear relationship with the solar activity or cosmic rays. It can happen in cycles of 7 years or 11 or 15 years. So the best way to look at that's still a mutant hypothesis, is that is like water on a ditch, right? So you have on the central part that is going with more speed on the walls. If you think that the walls are, for instance, sunspots or X radiation, solar X radiation, and on the other hand, cosmic rays, it gets to a moment when it enters into turbulence, Reynolds effect, Reynolds number effect. When this turbulence happens, what is that it generates in a very short time, not more than, let's say, in the peak part, no more than a few weeks, and then you have tremendous impact that generate globally, well, not globally, but almost globally, a lot of butterfly effects, which means that in some places where are wet, they become dry, and the others that are dry become wet, right? So this is a scheme of a cut about the Peruvian Pacific, the desert, the Andes, and the Amazon. That system makes the cold part of it, it's called La Niña, which means there is a thin ozone layer, and the UV gets and makes the job. But the job is, okay, the job is endothermic, and the reverse is when El Niño happens, that is exothermic, and O2 is released, and because of the chemical reaction, the composition that UV makes on the H2O2 or the hydrogen peroxide generated, and then thickens the ozone layer. And this is the cycle. Niña, Niño, Niña, Niño. That happens every year. It's a seasonal thing until it gets into this type of turbulence, which is the big Niño. And you see at the bottom part the phytoplankton character. I mean, it's big in the Niña, it's building up. In El Niño, when it gets hotter, obviously it's reduced, and then it goes back until it gets... This is a graphic about what happened this year. And in day zero, which was October 2036, the dark blue is the thinnest ozone layer. As you see there, in the day 60, there is in the Peruvian coast more thin part. And in the day 120, which was in February, what happened is that the Amazon system, the Amazon evaporation system, and the Pacific because of the Andes, they never met. But as there was a lot of activity in this turbulence, they got equal and the two systems got together. And there was generated a big Niño. It costed a lot of millions, $30 billion in 2 weeks. And then, on day 150, the ozone layer thickened because the oxygen of the reaction went up and the HV, the ultraviolet, started to make ozone. This is a graphic that is a classical one, that an 18% reduction in the ozone layer increases UVB by 28%. So it is not linear, right? And it's enormous energy coming on. You can see here the Niño part, where the sea temperature is raised, these are anomalies, and the chlorophyll is big. And in the is scant because it affects the sea temperature, affects the chlorophyll. In the Niño time, which is endothermic, the sea temperature, the anomaly goes down and the chlorophyll increases. So it's a kind of accordion that acts every year, seasonally, until there comes break-even point enters into turbulence and develops the big Niño. Here is the effects of temperature. If you see on the right, in the first one, the hot point is in Brazil. Then this keeps expanded till February, where the hottest spot is in the Peruvian coast, because the two systems got together, and then they divorce again a few months later. In April, the top part was in February. In April, it started the two systems to separate, and in September, it was completely separated. There is we think there is a misconception of ozone, which says it's a kind of a cloud that moves around. We don't think so. We think that is a system by which there is an exchange of acquisition during the cold times, the near times of oxygen, and a release is obvious. I mean, it's a gas, and also is decomposed from the hydrogen peroxide, and it makes a system that is localized. These big disturbances make us think that what we are talking about is a self-sufficient system, self-organized system. Okay. These are the butterfly effects of El Niño event. I am talking about the big Niño event. Resuming our process, the one we are doing, we are saying is to capture incoming UV energy in a hand-storable solid via water, which becomes an alternative neutral energy source, a new frontier. I mean, nobody has looked to UV as an energy resource because simply they don't have the condition we have. I mean, it's, okay, let's take here, I mean, high is 3. For us, normally 17. That's a big thing. Well, our process is to capture incoming UV energy in a hand-storable solid. The backbone of our system approach is the concept that water is a self-organized system. Now, we think that if we relate all the things I have heard and the works of Jerry, I mean, there are enormous coincidences with the big ones and the small ones. We are talking the same thing. It is what we used to call ice likes, right? And that's the reason I contacted Jerry. And the easy workings, we are not thinking about the electrical part, but thanks to the work of Jerry, we change the way we structure the brine, right? We use calcium chloride initially by absorbing water from the atmosphere. And it took so many days to get hydrated that we didn't have the patience, so I put ice on that. I made the hydration of the salt with ice, and the results were fabulous. Why? well, we need to interpret that because there was a transition, there was no liquid going on. It was from the ice directly to the hydration without entering into a liquid state. We have tested that with other experiments we did for a contest at NASA about Mars, and we have found that maybe the triple point is not a point, but it's an area where there is an exchange and where the normal thing are the crystal and the gas. And maybe the liquid state is not a state, but a mixture of both. Our experience is that when we started to prepare with ice our solutions, it became what we call, maybe crazy to name it, we say it's a marangonized solution for the marangoni effect, the tears of wine. So it is, the salt keeps the hydration. Within the hydration are easy material. It's not normal water, it's easy water or ice-likes. The reason being that if you take an anhydrous salt, calcium chloride, and you put water, it steams out. But with ice, it doesn't happen. Because what happens in our concept is that the conversion of liquid water into hydration water liberates energy. But if it is ice to ice-like, there is not such a liberation of energy because it's not needed. It's not liquid. Well, that is in speculation. I want to thank a friend of mine, Joseph Sennens, who is a Belgian, and Jerry for his kind invitation. That's it.